All right, welcome to page 4, where we're going to talk about differentials, what a differential is, and how we can actually find it. So basically, what a differential is, it's just another use of derivatives that we can use to approximate certain values of our function. So just like linear approximation, how that is approximating values, so is differentials. All right, and so to best describe differentials, what I'm going to do is I'm going to draw a little coordinate plane, a 2D. You have one above, and it's pretty good, but I feel like sometimes there's just a little bit too much going on for the first one. You're not really understanding things. So I'm going to draw 2 points. If you notice, there's a Q already there. So when I was recording the first time, the iPad shut down and it erased, or it stopped the video, and I didn't want to have 2 videos going on and off. So I'm just starting the record of this. So hopefully this doesn't. It's mainly because I was talking without touching my iPad. So here we have the 2-dimensional system. So we have a curve from P to Q. And what we're going to do is I'm going to draw a tangent line at P. And so what's in red is going to be my tangent line. All right. Now, when we talk about differentials, there's a difference between dy and delta y. Now, whenever you have your independent variable, so our x is going to be our independent variable, and we're going from 2 points, from point P to point Q. Well, your x just changes by delta x. So your deltas is just your total change in your independent variables. So from x to x plus delta x, that difference, that total change is the total change of delta x. So all we did was that if I ask you what's that length there, it's just delta x. So, but for our y's, it's different. For our y's, there's going to be 2 parts. We could have dy or delta y. Dx and delta x are going to be the same because, again, those are independent variables. But when we're talking about the dependent variable, your dy and your delta y are going to be different. So to explain that, you need your tangent line, and then I'm going to draw a horizontal line, and that's just going to represent the initial y value. All right. The total change from your initial y value at Q to the tangent value at Q, that's dy. So that's just the change between your initial y and where you're at on your tangent, either plane or tangent line. In this case, tangent line, 2-dimensional, but tangent plane in 3-dimensional. And then delta x is, again, the same thing it is with, delta y is the same thing it is with delta x. And that is, it's the total change from your initial y value to your now y value at Q. So that's delta y. So delta y is again, total change just like it is in x, but your dy is different because it's the dependent variable. And so your dy is different from your delta y. Dy is distance from, your initial point P to your point Q on the tangent line. So the distance between, your point and the tangent line, or delta y is just the total change from your initial point P to your point Q. Now, we call that, that would be the differential on a 2-dimensional coordinate system. I doubt y'all learned differentials in Calc 1 and Calc 2, mainly because differentials are not really on the A, B, and BC exam, so you probably haven't seen this. Maybe you have, I'm not sure. But it is very useful in physics and engineering, so I know most of you are in the MESA program, so definitely wanted to go over this. So when we're talking about the 3-dimensional coordinate system, we have 2 independent variables and 1 dependent variable, dependent being the z. So now dz is going to be our differential or our total differential, and it's defined by instead of having, you know, just one derivative, now we're going to have two, one with respect to x and one with respect to y, are partial derivatives. And dx dy is just going to be the total change in your dx and your dy. And I want you to notice down here, x equals dx, that's delta x is equal to dx. It's just the total change in your x's, and delta y is equal to dy. Those are going to be the same. The only thing that's going to be different between your delta and your d is going to be dz and your delta z, because that's the dependent variable. And so here you can see, you know, if we're going from, you know, this point to that point on our you know, for our surface, where, you know, this is our initial point, and then here is our second point, and we want to find, okay, what's the differential there? Here you notice what's in orange is the tangent plane. So the difference between, okay, so the difference between our point, you know, at the original z and the tangent plane is going to be dz. The difference between our initial point and our point on the actual surface is going to be delta z. And so here you have the same concept with three-dimensional, and you have the plane. And so we're just going to use this to help us determine, you know, how we can approximate certain values using differentials and using you know, our total distance and our total change. All right, and using our partial derivatives. So for 32, if z is equal to x squared minus xy plus 3y squared, and xy changes from 3, -1 to 2.96, -0.95, we want to compare the values of delta z and dz. So the first thing we're going to do is we're going to go ahead and find what dz is. I'm going to keep the top above, just so that you see this is what we're going to use to find dz. So in order to find dz, we need the partial of x and the partial of y. So I'm going to go ahead and find the partial of x and then do the partial of y. So using the partial derivative, we're going to have 2x minus y. And then we'll do the partial of y. You know, I'm going to go ahead and find the value there too, so the partial of x. And then I'm just going to use my two values that I have to find what my partial is going to be. So at 3, -1 is my point. So at 3, -1, we're going to get 6 plus 1, so 7. Then I'm going to find the partials of y. And so that's going to be -x plus 6y. So substituting that in, I get -3 minus 6. So that I'm going to get -9. All right, some other things that I want to solve for. I want to find out what delta x is and delta y is. So delta x is just the change in the x's. So what's the total change from 3 and 2.96? The total change there is going to be -0.04, because we start at 3, -1, and we're going you know, back on the x, so -0.04. And then for y, we're starting at -1, but we're actually going up on the y. So your delta y is going to be positive 0.05. All right. So now what we can go ahead and do is we can go ahead and plug this in. And so dz is going to be equal to, and so I have my partial of x, which is going to be 7, times my change in x, which is -0.04, plus my change in my partial derivative of y, which is -9, times the change in y, which is 0.05. And when I do the math there, we're going to get -0.073. So that's going to be my dz, my differential or total differential. Now, when I want to find my delta z, delta z is just the total change. So I'm going to take my function at 3, -1, and I'm going to subtract that by my function of, I'm sorry, not 3, -1. We want to do our value first, so 2.96 minus 0.95 minus f of our initial value, 3, -1. So we just want to find the total change from our initial to where we went. So when we're looking for total change, so our delta z, we're going to get, we'll just plug f into our function. So we're plugging f into, or we're plugging both values into our function there. And so when we do that, we're going to get 2.96 squared minus 2.96 times -0.95 minus 3, sorry, not minus, but plus 3 times 0.95 squared, and then minus all that. 3 squared is 9, -1 times 3 is -3, so plus 3. And then we have 3 times -1 squared, so 3 is another plus 3. And so our delta z, we're going to get -0.718.